So already in my previous video, I was discussing about this particular pole zero plot of the digital integrator, and I have shown you the pole zero plot of this, which we are getting like this, and at zero frequency we had pole. Okay, and as you know that pole always try to amplify the gain or increase the gain, and zero always try to decrease the gain. So as at zero frequency one pole is present and pole always try to increase the gain, so we are getting very high gain at frequency corresponding to zero, which we have seen in our response curve. Also in the magnitude response we are getting at zero frequency very high magnitude, or we can say the gain is very high. Right now what happens, so that it decreases very rapidly? We have just seen what is the reason behind that rapid decrease after as we go from 0 to pi. See, try to understand it very clearly. And now you just consider, if we move from 0 to pi, then what happens? Suppose consider here one particular point is there. From 0 I have moved a little bit towards the pi. Okay, now consider this particular point. Now this particular point goes at a far from pole, and it is also there is also a distance in between this point and 0 also. So now you just observe, pole is trying to increase the gain, but 0 is trying to decrease the gain. When we were in this particular point, their pole has huge dominant power, because there itself pole was present, so that it was not counting the effect of 0, and it was amplifying by a huge amount. But as we are going from 0 to pi, the distance from the pole increases, right? As the distance from the pole increases as we move from 0 to pi, so the effect of dominant power of pole also decreases. So that what happens now, slowly by slowly the power of 0 will also start affecting on the system. Now what is the power of 0? 0 decreases the gain, and as we are moving from 0 to pi, so distance from the pole increases, starts increasing. Okay, and the effect of 0 of the system also starts coming up. So as a result, what will happen? The gain will start decreasing, so that after moving from 0, if we move somewhat amount, we will get a decrease. So that the graph, you just see the magnitude response here. I started drawing this particular part, there is a decrement in the gain. Now if you move further from 0 to pi, then what will happen? Distance from pole to that particular frequency point will increase more, and distance from 0 will basically in that case, when we move from 0 to pi, then for that particular point distance from pole will increase, and distance from 0 will gradually start decreasing. So as a result, 0 will affect more and more than pole. So as a result, what will happen, if we come at suppose this particular point here, this particular frequency point has more distance from pole, so pole has lesser power on this particular point, whereas 0 is still working. So as a result, what will happen? The gain will decrease much. And as we move further, suppose consider somewhat point here or here or here. See, for every point on this side, whatever you consider, 0 is closer corresponding to that point than the pole. Okay, suppose you consider this particular point, then here see 0 is closer, so 0 will affect more than the pole. Pole will try to increase the gain, but 0, as it is closer, the effect of 0 to decrease the gain will be more, and as a result, as we move from 0 to pi, the gain or the magnitude response decreases, and at 0, that is at pi, what will happen here? If you consider this particular point here, 0 distance with respect to 0 is very less compared to distance with respect to pole. So as a result, we will get a very high amount of attenuation. Okay, so for this reason we are getting this kind of magnitude response curve. I hope you have understood the reason of getting magnitude response like this, and it is quite clear this is nothing but a low pass filter, because at lower frequency we are getting high gain. As the frequency increases, our magnitude response gain is decreasing. Right now, another concept. Suppose what we do, we add one coefficient here. Suppose this was our difference equation, y of n is equal to x of n plus y of n minus 1. Now suppose we want to add one coefficient a, multiply by a, then we will be getting this kind of difference equation, y of n is equal to x of n plus a into y of n minus 1. And if you take z transform and calculate the transfer function, eventually we will get y of z by x of z is equal to 1 by 1 minus a into z to the power minus 1. Right? Now see what will happen. Now try to understand. So now in this case our h of z is 1 by this particular term, right? So let me copy this, control V. Now I want to calculate pole. So 1 minus a into z to the power minus 1 equal to 0. So from here we can get 1 equal to a into z to the power minus 1. Okay, right? So now we can simplify it further, that z to the power minus 1 equal to 1 by a, right? So we can say z equal to a. Okay, so now our pole is at z equal to a. Okay, now what should be a value? What we should take? Greater than 1, less than 1, or what? Obviously we have to take a value lesser than 1. Okay, why, you may ask? Very simple. See here, this was our difference equation, right? Y of n is equal to x of n plus a into y of n minus 1. So we are getting h of z as 1 by 1 minus a z to the power minus 1. So numerator coefficient is 1 and denominator coefficient will be 1 and minus a. Suppose I take a value greater than 1, 1.5 I am taking. Now you just observe what we are getting in the pole 0 plot. If we do like this, we are getting one pole outside the unit circle, which is making our system unstable, right? So that what we should take always a value lesser than 1. Suppose I am taking 0.5. Okay, it is quite clear that our pole will be situated inside the unit circle and we are getting a stable system. So what should be a value? Less than 1, less than or equal to 1, to get a stable system. Now what will happen to this? Now you have just seen, if we take a value lesser than 1, like I have taken a value as 0.5, then we are getting our pole 0 plot like this, right? Now what will happen, just try to think. In this case also you will get the magnitude response like earlier, low pass filtering action only. Explanation is same. Like what? Here here if you consider one point corresponding to this point, pole is nearer compared to 0, so pole will try to amplify the system response or increase the gain in the magnitude response. And as we move further from 0 to pi, the distance from pole to that point will increase and it will closer to 0. So as a result, as we know that 0 try to decrease the system response, so it will decrease. So again here also, starting from 0, if we move to pi, we will get one low pass filter type graph where magnitude response gain will gradually decrease from 0 to pi. But here one very important point to note, which I want to show you. Suppose you consider one point here, that is at DC or omega equal to 0 or angle 0. Compare the previous case. Here when we were considering digital integrator, see, pole itself is situating on that point where DC equal to 0, that is omega equal to 0. Now when we are adding one coefficient a, the pole is shifting towards the left hand side. Now the pole is not at this particular point, right? So pole cannot amplify the particular magnitude response as earlier, because here is one distance. Initially in the previous case, in the digital integrator case, if you consider any point on unit circle at omega equal to 0, there itself pole was present. So distance between that point and pole is basically 0. So as a result, what was happening, that pole was highly dominating and it amplified the system very much. But now if you consider at any point on omega equal to 0 on unit circle, that is here, now here pole is not present. here little bit distance is there, so as a result pole cannot amplify the system as much as earlier, although it will obviously amplify because the pole is nearer with respect to this point with respect to 0, because 0 is at further, we can see itself pole is nearer, so effect of pole is more, obviously we will get high gain at 0 or DC frequency or DC or at 0 frequency, but it cannot amplify like earlier. Earlier what we have seen? Earlier here we have seen, if we put here -1, that is digital integrator, we were getting the magnitude response gain at 0 frequency very high, close to 600. But now if we consider this particular system, for 100% sure that the gain will be lesser than 600. Let us visualize that. I told you our coefficients will be numerator equal to 1 and denominator will be 1 and minus a, and a has to be taken lesser than or equal to 1 for stable system. Let me take 0.5. Okay. Now let us check control A, evaluate selection. If I do, see what kind of graph we are getting. We are getting low pass filter type response only, but now see the maximum gain offered in the magnitude response. It is 2. Initially it was 600, but now we are getting only 2. Okay, so we can understand why this is happening, what is the effect of shifting of pole towards the origin. Okay, so this is all about the discussion for today, and one thing is quite clear for us for the time being, which is very important conclusion, that this is the general expression of a low pass filter, which is y of n equal to x of n plus a into y of n minus 1, and the transfer function is h of z equal to 1 by 1 minus a into z to the power minus 1, where a has to be lesser than equal to 1 for a stable system. All right, I hope you have understood this. Make a clear idea, intuitively try to feel that why we are getting the response like this. I hope from the picture itself it is quite clear. This is all for my this video. Thank you for watching.